Hi everyone, this is Mohammad, and today I'm going to be talking about the use of machine learning in mineral potential mapping. And this is a topic that was actually covered by Jeff. Jeff actually gave a really neat talk last week, and this is going to be a sequel to Jeff's talk, but I'm going to be mostly focused on overfitting, which is a common problem while applying machine learning algorithms for mineral potential mapping or a predictive bedrock modeling. This talk has been organized in 4 sections. In the first section, I'm going to be giving an introduction of machine learning methodologies and their algorithms. So then I'm going to be talking about how we can use these algorithms for mineral potential mapping. And I'm going to support that with 2 case studies. So machine learning refers to a series of different algorithms that are commonly used for pattern recognition. And what we do is that we introduce our algorithms to different data sets, and they really kind of go through our data sets and interpret them for them. And what they do is that they recognize some patterns. Some of those patterns are really subtle, and we need to use sophisticated tools and methodologies in order to recognize those. And some of them are really important. It is actually finding its application in many different branches of science, as well as geology and mineral exploration. And this is going to be the topic of our talk today. And so we have different types of machine learning processes, but the majority of them are focused on classification, regression, clustering, and dimensionality reduction. And we do have a variety of different applications for these methodologies in mineral exploration. For example, dimensionality reduction is commonly used in remote sensing and also in processing and interpreting geochemical data sets, and also pretty much the same for the rest of other type of algorithms. But we have different categories of machine learning algorithms. We have supervised learning, unsupervised learning, semi-supervised learning, and other types of learning procedures. But today, I'm going to be mostly focused on the first 2 categories. So what makes the difference between 2 sets is the use of some sort of samples, which we usually refer to them as labeled samples. So labeled samples are some samples that are actually tagged with certain features. For example, a mineral deposit or a mineralized zone can be considered a labeled sample, because we know for sure that that is a location in which a mineral deposit exists. So we can go ahead and use our labeled samples in order to train and calibrate our models. And then we can kind of really apply the calibrated model to either classify or predict some features of our data sets. So the difference between these 2 types of algorithms, as I mentioned, is in the use of labeled data sets. So supervised learning has regression and classification applications. By regression, I mean sometimes we have to make some predictions. But classification is referred to the process of categorizing some data sets. And this is pretty much the same for clustering. The only difference is that in clustering, we do not use labeled samples. And also, I did mention some applications of dimensionality reduction. It refers to the process of reducing the complexity of our data sets by reducing the number of our variables. And it is really useful in geochemistry and remote sensing. So what we do in supervised learning methodologies, we first start by selecting our labeled samples. And this is, I think, is the most important step in developing supervised learning algorithms, because labeled samples should be selected really carefully. But then we have training and testing procedures, and after that we have the application. So in this chart actually kind of really represents that in a really neat way. So first, we start by selecting our labeled samples. Then we divide our labeled samples into two categories of training and testing. What we do with training data sets, we try to develop our model, and then we try to calibrate our model with our validating set. So if the model actually passes our test, then we can actually go ahead and use it for predictive modeling from our unseen data sets. And then here I want to start talking about the application of machine learning in mineral potential mapping. So first, a brief definition of mineral potential mapping and what it is actually. So mineral potential mapping refers to the process of integrating different types of data sets in order to delineate some exploration targets. And what we do with mineral potential mapping, we kind of really try to reduce the search space for mineral exploration. And by reducing the search space, we are reducing the risk and cost of exploration because we know for sure that exploration is really expensive, and we try to minimize kind of really those expenses. And MPM is a really, or mineral potential mapping, MPM is the abbreviation for it, is really critical right now because we know for sure that we need some resources of critical minerals, critical metals, and also precious metals. And for these, what we have to do is to kind of really do some mineral potential mapping. It could be really helpful because, as I mentioned, it can help reduce the risk of mineral exploration. So this is what I think. So I think actually mineral potential mapping has three main components. So the first component is the data sets that we have. So we have different types of data sets. We have geophysical data, we have remote sensing data sets, and also geological maps. And with different types of data sets, we do need people with different expertise to try to actually interpret them and recognize some anomalous patterns out of those data sets that are associated with our mineral deposits. So besides data processing and people with those expertise in different branches of geoscience, we need data scientists in order to analyze different types of data sets and recognize some patterns associated with mineral deposits. So what data scientists do, they use algorithms in order to kind of really recognize those patterns. And we have two major types of algorithms. So we have conceptual and empirical frameworks that are our mathematical frameworks for recognizing our patterns, which are our exploration targets. So each type of algorithm actually comes with its different application. So in short, we use data and expertise in order to develop some evidence layers, or as we call them, predictor variables. Then we need to kind of really weight and synthesize those predictor variables in order to recognize some patterns. And this is an example of a mineral potential map that has been developed. And what is really important is how we process our data sets. So, and this is the geological framework that we should apply. So the purpose of using a geological framework is to help translate the data sets that we have into a number of mappable exploration criteria. And those exploration targeting criteria are our evidence layers. So what we should do is to just try to define the main processes that are involved in the development of mineral deposits. So these processes are usually drivers. Drivers kind of really trigger the generation of fluids that are important for us. Sources are where, and actually the places that give birth to those ore-bearing components and fluids. And we need some pathways to help channel those fluids. And of course we have, and we do need some trapping mechanisms. So trapping mechanisms are essential because they help deposit mineral, they help deposit ores from the ore-bearing components. And what we do is we try to simplify those processes by defining them and actually try to kind of really translate them into some mappable exploration targeting criteria, either directly or by using a proxy. And we can develop different types of predictor variables or evidence layers. And this is something that we'll be talking about in more details shortly. So we have different types of predictor variables. We have binary variables. An example of them actually is illustrated here. And we have multi-class and continuous variables. So each type of variable comes with its pros and cons. We know for sure that if we use binary variables, we try to simplify our modeling method. But what we do is that we are risking of using some sort of information by using binary variables. With using multi-class or continuous variables, however, we kind of really add some complexity to our system, but we try to keep our information. So as I mentioned before, we have two types of algorithms. So we have conceptual algorithms, and also we have empirical or data-driven algorithms. So both algorithms are really useful, but actually it is really important where to use these algorithms. Empirical algorithms are usually used when we have enough data set, and we have, more importantly, enough data set in order to train and validate our models. And this is where we can use machine learning algorithms. So empirical frameworks are usually useful for brownfield areas or areas in which some mineral deposits have already been discovered, and we can use them as our labeled samples. So we have different types of empirical or data-driven algorithms, but perhaps the most popular one is the weight of evidence methodology, or the use of Bayes' theorem, which is quite really popular. And also we have machine learning methods. So we have different types of machine learning algorithms. We have simple regression techniques, such as support vector machines or support vector regression. And we have more complicated methods, such as regularized regression, boosting, bagging, and neural networks or deep learning. So these methods are useful, but it is really important to note that we need to be really careful while applying these methodologies, because they have, of course, some sorts of limitation. So here we're going to be talking about why we actually kind of really use machine learning methodologies. So there are a couple of reasons why we are really interested in using these algorithms. Perhaps the most important one is that the patterns that are associated with the formation and discovering of mineral deposits are far too complicated to be modeled and recognized with a simple Bayes theorem. And also nowadays, we don't have sufficient exposure. And this is actually the problem that we're having in Canada, because the majority of our lands in Canada are actually covered with glacial deposits. And that really complicates the exploration for sure. And because of the fact that we have different types of data sets, we have tons of different variables to deal with. And as a matter of fact, and as a result, we need some methodologies to be able to handle those complexities of our data sets. And in short, this is how we develop mineral potential maps. In brownfield areas, we first start by using our data sets and our geological knowledge to define a number of predictor variables or evidence layers. Then we try to find some labeled samples. So with labeled samples, we have positive and negative sites. So positive labeled samples in regional scale are the location of our mineral deposits. In the positive scale, we can use the location of our drill cores, for example, the location of our mineralized zones in order to define our positive sites. But for sure, defining negative sites is really challenging because negative sites should be some sites that are definitely non-mineralized, and we are not sure, we cannot make sure until we actually see the land and analyze it. So defining negative sites is something that is by nature really prone to some uncertainties, and we need to be really careful about it. But the first step in defining negative sites is to try to define a number of random samples, because unlike mineral deposits that usually form some clusters, random sites should be distributed randomly in space, and they should actually adhere to a random spatial distribution. Then after defining labeled samples, as I mentioned before, then we should go ahead and split them, try to develop our model and can kind of calibrate it, and then use it in order to predict our unseen data sets and develop some predictive models of mineral prospectivity. So we have some limitations in using machine learning algorithms and for mineral potential mapping in general. So errors and uncertainties, they actually affect our model, and overfitting is one of the common errors that we have, but I actually have separated it from other errors because this one is the topic of today's talk, and this one is going to be an important one. But this is actually how I'm going to define overfitting. As I mentioned, the first thing that we should do is to try to define our labeled samples. So these are a suite of our labeled samples. What we want to do here is to simply try to predict the height of a bunch of samples on the basis of their weights. And so the first thing that we have to do is to try to divide those samples into two categories. The blue category is our training data, and the green category is our testing or validating data set. So then we have to really feed two different types of models to the training data set: a really simple model, which is a simple line, a straight line, and a complex and complicated model. Then we have two definitions in here. The first definition is bias, which is defined by the ability of model to predict the data set it has been trained with, or the training data. And variance is the ability of our model to predict testing data set. So for the simple model, we do have a small amount of bias, and also we have some variance. But here for the complicated model, we almost have no bias, but we have a lot of variance. And variance is really severe in this complex and complicated model. So here is where when we say that our model is really overfit. So overfitting is defined by the difference between variance and bias, and this is a really common problem. But we should try to minimize it because as we all can see, when we have overfitting, our model is not going to be really applicable, and its application is going to be really limited. In other words, our model is going to be totally useless when our model is overfit. But today we talk about why we have overfitting in our models and how we can overcome this common problem. So overfitting comes from a number of problems. The first one is that our models might be too complicated. But the most important cause of overfitting is our labeled samples, because the problem ends up being is that we do not have enough labeled samples to train our models. And so what we have to do is to try to, if we can, try to increase the size of labeled samples. And this is something that we are trying to explore in our case studies. And sometimes the complexity of our model is associated with our predictor variables. As I mentioned, if we use binary variables, we can simplify our models, and as a result, we can reduce the complexity of our input variables. And also, it could be also associated with other causes. So a little bit about the sources of errors and uncertainties. In short, different stages of mineral potential mapping are really vulnerable and prone to the problem of overfitting and error. And this is something that we have to be really careful about. Data collection, processing of data sets, development of evidence layers, and also even some uncertainties that are associated with our modeling methods. These are all some aspects that cause problems for our models, and we should try to really minimize them. Some of them cannot be really prevented, but as I said, we should try to minimize them as much as possible. So evidence layers, which are the topic of today's talk, we know for sure that they are some major sources of uncertainty, but with different types of frameworks, we also have different types of uncertainties. With data-driven or empirical frameworks, the problems are associated with our labeled samples, and the fact that we can have multiple training methodologies as well as multiple tuning methodologies. So these are all problematic, and we should try to really reduce them. But some of these uncertainties cannot be avoided, and what we do is try to measure them. By measuring them, we are using them for our benefit, and this is something that I'm going to be talking about in our case study. So I'm going to start our first case study, which is the predictive model of mesothermal gold in Sturgeon Transect. And what we want to do is try to handle overfitting in our model. So this is the goals that we have in this case study. So the first goal is to for sure delineate some exploration targets. Then what we do is try to assess the effect of sample size for mineral potential mapping and on the problem of overfitting. And after that, we try to assess how variable type can affect overfitting in MPM. So a brief introduction about the Sturgeon Transect. So the Sturgeon Lake hosts a number of mineral deposits. So some of these have been interpreted as orogenic gold deposits or mesothermal gold deposits. So the majority of rocks are pre-Cambrian in age, and we are dealing with a greenstone belt. But today I'm going to be mostly focused on the data analytic part of the talk, but just a little bit, I want to just introduce mesothermal gold and how we actually went ahead and defined our exploration targeting criteria. As I said, we should try to define some main processes that are involved in the development of our mineral deposits. So the first important component and the first important process is the source. We know for a fact that mesothermal gold is associated with our Archean deep continental crust, and this is where actually our fluids are sourced, and the process that really triggers the generation of these fluids is probably the folding and some thrusting and squeezing of different layers. So structures are really important in the exploration and also in the formation of mesothermal gold systems, because we know for a fact that structures provide some pathways for channeling these fluids. And this is a common example that actually this is a model that has been presented in many talks. So what we have in here, so this is a seismic section of Western Ontario. And what we have, we can see that we have some intact crust in here. And this is where probably our ores, actually ore-bearing fluids come from. And we can clearly see that these have been transported with some channels and with some pathways. And those pathways are faults and fractures. So structures, in short, are really important for us. The contacts of different lithological units are really important for us, and we should try to make the use of them. So as I presented in my previous talk for metallurgs, we used a number of different data sets. So we have our bedrock map, we have our gravity data sets, and we have our geochemical data sets. We also have our magnetic data set, airborne magnetic data sets. So what we have done is that we have tried to just define a number of different predictor variables. This is what we actually initially developed and initially proposed for this study area, but we went ahead and measured the spatial association of these predictor variables with our mineralization. And what we found was that the majority of these predictor variables were not really robust because the spatial association between them and mineralization was not really significant. So this is a way that we have used in order to measure that spatial association. And what we have done is that we have used a receiver operating characteristics curves. And these are commonly used for measuring those spatial associations. So the higher the area under the curve is, and the maximum area is 1, and the closer our number to 1 is, the more significant our predictor variable is. So on the basis of that, we reduced the number of our predictor variables and came with this solution for that. So we really reduced the number to just 11 predictor variables. And we tried to assess the effect of variable type in mineral potential mapping. For this, first we use a combination of different evidence layers. So as we can see, we have different types of evidence layers in here. Some of them are binary and some of them are continuous. But in the second experience, we went ahead and developed only binary variables. And so in this way, we were able to assess the effects of using binary variables for our modeling method. So we have different variable types. So we have some bedrocks that are really important for us. These bedrocks can be either associated with our host of mineralization or the source of our mineralization. So all of them are really important for us. And as I mentioned, structures are all important. So contacts of different lithological units are really important for us. We try to use the stratigraphical horizons that have been defined in the area in order to define some groups. And we measured the distance from those contacts in order to develop some predictor maps. So we use the gravity data set because we know that our bedrocks that kind of really host gold mineralization are heavier, so that can be used as a proxy for defining those rocks. And also we used magnetic zones because those zones are also associated with our mineral deposits. And also for sure, we used some sort of faults that are associated with our mineral deposits to predict, to actually use and define yet another exploration targeting criterion and evidence layer. So this is just an example of different types of evidence layers that we have used. So for sure, this one on the left side is our gravity model. And we know for sure that some of our gold deposits are associated with anomalies of this gravity data, showing that this one could be a really useful and important one. So I think that one is really among our important predictor variables. And also we have some host routes. So these are some examples of our binary predictor variables that we have used. So as I mentioned, we have conducted 2 experiments with different types of evidence layers. So the first experiment was conducted by different types of evidence layers, including binary and also continuous layers. And the second experiment was only conducted with just binary variables. And in both experiments, we have used 2 categories of labeled samples. We know for sure that we have some mineral deposits and some mineral occurrences in our study area. So mineral deposits for sure are those deposits, those ore bodies that have measured tonnage and grade. But for a majority of occurrences, these measurements are not really available. And that's why, so we have used 2 categories of labeled samples. So for both experiments, we have used just mineral deposits once for training our model. And then we have used both deposits and occurrences for training and validating our models. And the purpose of this work and this activity was to see how an increase in the size of our labeled samples can can really affect our model in a positive way. So this is an example of labeled samples. This was just to show an illustration of how we went ahead and define our labeled samples. So here is the location of our mineral deposits. So these are our positive labeled samples, and they are tagged with a target variable. So the value of this target variable for these mineral deposits is 1. And for these negative samples, which are randomly distributed in space, the value of our target is 0. And this is the value of different exploration targeting criteria. And this is just an example that I have demonstrated here. And so the question is how we developed our binary variables. So we know for sure that some of our variables are originally continuous. And so what we have to do is to try to define significant binary variables. For this, we have used the weight of evidence procedure. So there is a t-value, and this is an example of using student t-values. Usually the maximum t-value defines the most important threshold for defining a categorical variable. And this is how we have selected our thresholds for developing those binary variables. And so, as Jeff actually explained in last week's presentation, we used random forest, which is a bagging procedure. What this method does, it tries to repeat itself using different subsamples of our training samples. And in this way, using different trees, it is actually a combination of different predictive trees, and as a result, it improves the performance of individual trees. So for today's talk, in the first section, we have used just random forests and as our method. So the random forest actually enables us to measure the importance of different variables. So here we can see that for different model types that we have used, so P11 is really important, and P11 is the distance from R faults, which kind of really stresses the importance of structures for our mineralizations. And also, we know for a fact that gravity is also really important. This is P9 and P5, which are some contacts of our lithological units, are really important for us, we know for sure. So these are actually the contacts or our banded iron formations, and this is actually rooted in the fact, the importance of this contact, that those banded iron formations can serve as the host for our gold deposits. So as I said, these are the results of different experiments that we have conducted. So we have come up with different models. The models are kind of really look like the same, but they're quite different when we try to measure their performance, but visually they are kind of the same. So this is our best model. This is the model for which we have used all of our samples, both mineral deposits and mineral occurrences, and visually actually it kind of really fits all of our mineral deposit and our mineralized zones. But we can see also some differences in the distribution of colors for them. So the pink color actually is associated with some anomalies that should be really important for us. So when we measure the spatial association of these models and when we measure the performance of these models, what we understand is that, as I said, the model for which we've used all of both deposits and occurrences is the most important one. So here, the orange model, which is the first experiment, the first experiment means using both binary and continuous variables, using a mix of different variables, and including all of deposit and occurrences for training is the most significant model that we're getting. And also here, the first model that we have used, for which we have used all of variables, are really important. So what we can understand from here is that using binary variables really did not improve the results of our modeling method. And this is something that is actually the opposite of the conclusion of some of the papers that have already been published. So this is not really controversial. This is actually rooted in the fact that our data set was totally different, our case study was different, and our model systems were different. And so for each case study, actually, we got to really develop our own strategy. So, and different case studies are not going to be the same. And when we measure the overfitting of different models, what we can understand is that the model that uses both mineral deposits and occurrences is the most effective one, because for sure, this has the minimum value of bias, variance, and also overfitting. And also the model that uses only binary variables actually works, that didn't actually work really good in this study. So what we can understand here is that increasing the number of labeled samples can really help reduce the effects of overfitting in mineral potential mapping. And so in our second case study, we have used different algorithms for mineral potential mapping and really try to answer the question that which methodology actually is the best. So I'm not going to go through the mathematical aspects of these methods, but what we've done is that we have used all of these methods that we can see here. I should have actually added a simple regression, because besides the methods that have been presented in here, we have used a simple regression algorithm as well. So for bagging, we have used random forest. For boosting, we have used AdaBoost and XGBoost, which is extreme gradient boosting. And we have used different types of regularized regression algorithms, but I only just used the results of one of them, because there were going to be too many methods. So for regularized regression techniques, I have used the lasso algorithm, and these methods really help overcome the effects of overfitting in mineral potential mapping, especially where we have limited labeled samples. And I have used a group of neural networks, which are group method of handling neural networks, GMDS neural networks. And these are multi-layer neural networks, and we can actually refer to them as deep neural networks. So, and this is the conclusion of what I have done. I've just demonstrated the final result of it. And what we can understand is that using the lasso algorithm, we were able to reduce the effect of overfitting. So the results of a majority of these methods and their maps were actually pretty much the same. But lasso was better regarding overfitting, and random forest was better regarding bias, and also neural networks were better regarding their variance. But in conclusion, lasso was the best method, but really liked the result of random forest. And why I really, the reason behind why I really like random forest is its simplicity. So it is not really complicated. For a majority of these models that we can see here, we need to tune tons of different parameters, and it can become really challenging and really hard. But random forest is really easy, and this is why this methodology is really popular, especially in mineral exploration. But our best method here was lasso, and this is the results of our lasso algorithm. And what we can see is that the majority of our mineral deposits and occurrences have been located in the anomalous zones that have been delineated by this methodology. So we also went ahead and really calculated the uncertainty of our model. This uncertainty is associated with the differences between different mineral deposits and occurrences that we have. And so with the measured uncertainty and also the measured prospectivity values, we can select some exploration targets that are less uncertain. And this is a concept that we've been working on, and this is going to be really useful because using this methodology, we have really delineated some exploration targets that are less risky. And yeah, so this is the result of our model. And that's really pretty much it. So that was my 2 cents on the work that we've done. So this is what we think. We think that each case study comes with its own strategy, and we need to strategize for that. And also the quality of our data sets are really important. And one thing that I really want to stress in here is that the key is to try to really minimize the uncertainties of our model, but we can never prevent them because there are multiple sources that give birth to different types of uncertainties, but we can definitely try to minimize them. And mineral potential mapping is a teamwork, as I mentioned, and this is something that should be done in a group, as we do in Metal-Earth. So thanks so much. That's pretty much it.
Thank you very much, Mohammad. That's great. That's an excellent introduction to machine learning and a couple of good case histories.
Thank you.
Some people are clapping in the participant list.
Yeah.
So we can ask questions different ways. If people would like me to read out their question, they can type it into the chat box. Or if people have a question they'd like to ask themselves by turning on their microphone, then they can raise their hand or they can turn on. So while we're waiting for people to think about their questions and to type them in, I have a question I would like to ask, and that relates to the data sets that you were using. So part of the Metal-Earth project involved collecting geochemistry data. Did you try and incorporate any geochemistry data into your machine learning?
Yeah, for sure. So initially, actually, we defined these predictor variables, and we have 3 different predictor variables that are associated with our geochemical anomalies from our lithogeochemical data sets. But because of the fact that those data sets, those samples were really sparse, you know, they were not really spatially coherent, and we ended up actually removing those data sets because their spatial association with our mineralization was not that significant. So as we can see, we have P12, P13, and P14, and these are our geochemical data sets, and unfortunately, they were the less effective models that we ended up developing. So we decided to actually delete those variables from our list, and in that way, actually, we really really improved our model, because we should kind of really try to minimize variables that are not significant.
And that's good. So I guess that's really because the geochemistry data was collected up the traverse and didn't really go off to the side, right? Is that one reason?
I think so. I think that's the reason. What do you think, Jeff? Yeah, perhaps actually Jeff is actually the best person to answer this question. So I'm not the best person for definitely answering this question. Yeah, but I think this is part of the reason that it was not actually that coherent for us. But I know for a fact that because those data sets were really sparse and we didn't have samples in all of our study area, that was actually part of the reason that it was not that significant for us. But for sure, some anomalies were associated with our mineral deposits, but we definitely need more samples. Yeah, from different.
Yeah, this is Jeff. Can anyone hear me?
Yeah.
There was a paucity of samples, and you're right, Richard. It was clustered around the transect, and dealing with geochemistry. And I'm not sure if Eric is here today, but can be a problem because we have to find out what's the best way of making a predictor map from geochemistry. Do we have to, if we have a paucity of data, we don't want to interpolate because that will add too much uncertainty through the interpolation algorithm. So what do? Do we buffer a zone of influence around each point based on field experience and looking at how far alteration it goes? So there's processing geochemistry can be very tricky when we're trying to produce predictor maps for input into the modeling procedures. And I've written a lot of papers on how to handle this. And if anyone's interested, you can contact me and I can send you those papers.
Okay, thanks, Jeff. And
Thanks, Jeff.
Any other questions?
I have a question.
Okay, go ahead, Frank.
Yeah, it's a suggestion and a question. Is maybe my suggestion for the talk, is it possible to have the speaker be able to see the speaker when he speaks? This makes it more personal.
Oh, for sure. Yeah. Sorry for that. Yeah.
No, I just that would just otherwise it just sounds like it's all I hear is a voice, where I can makes it more personal. I can see the speaker speaking.
Yeah, sorry for that. You know, I wasn't in my office today, and so I decided to just
No, that's okay. My question is, how would you be able to test how well the predictive modeling works in the future? Do you have to somehow distribute your predictive modeling and then see if exploration companies will explore or drill your area to see how well it works? How will you know how well it works? Because right now you're working from known deposits and showings and going backwards, making everything fit or see how well it fits. How do you predict for unknown areas in the future?
Yeah, that's actually a very good question. And so the purpose of mineral potential mapping is to introduce some targets, especially when actually we are developing some mineral potential maps for regional scales. And this is something that usually governments actually do, mineral potential mapping, because geological surveys, for example, they need to develop some mineral potential models. And this is what that they later actually give to private companies, I think. And this is for private companies to follow those exploration targets and invest on them and try to come up with some solutions for those exploration targets. But regarding testing, as I mentioned, so we have kind of validated our models with some mathematical approaches. And those approaches were the receiver operating characteristic curves as I represented them. And so here we have our receiver operating characteristics. So this is an example of the use of receiver operating characteristics. So as I mentioned, if our variables and our models are correlated with our mineral deposits, what it shows that they have worked well actually for our model, and otherwise they haven't worked really well. So we can kind of really measure their association with our known mineral deposits and occurrences. If our models are able to predict our mineral deposits or occurrences, we can say for sure that, okay, so this is going to work. And this was something that our talk was mostly centered on. We talked about the problem of overfitting. So overfitting is for some models that are really not applicable, you know, in the real usage. But when we try to prevent overfitting, our model is going to be really realistic. And this is what we really try to minimize in our study.
Hey. Any other questions? Or questions? Okay, well, so Jeff mentioned Eric's name, Eric Grunsky, and Eric Grunsky is going to be giving a talk on the use of geochemistry, and that talk is going to be in 2 weeks' time on October 18th. So we'll look forward to that as a follow-up to this particular talk. So now I guess I'd like to thank Mohammad and thank everybody for tuning in, and we'll have another seminar later.
Thanks so much.